Assalamu alaikum all of you. Uh, Today is our lecture uh, based on eigenvalue and eigenvectors. Okay. Talal, Fahad and Sultan. Only 3 persons are present. So today is our lecture based on eigenvalues and eigenvectors. Okay. So I'm going to upload the PowerPoint slides. So today is our lecture based on eigenvalues and eigenvectors. It is week 8. So now we are going to proceed. Okay. So the definition of eigenvalues, as you can see, there are the definitions of eigenvalues. A non-zero vector X is an eigenvector or characteristic vector of a square matrix A if there exists a scalar lambda such that Ax is equal to lambda x, then lambda is an eigenvalue. Then lambda is called the eigenvalue. Either we can say eigenvalue or we can say characteristic value, characteristic equation. So of a, both the things are same, eigenvalue or characteristic value. So the zero vector cannot be an eigenvector. Even a0 is equal to lambda 0, but lambda is equal to 0 can be eigenvalue. So lambda is equal to 0 can be eigenvalue, but it cannot be eigenvectors. So there are some small questions. Show x is equal to 1 is an eigenvector for a. So there is a there is a small matrix, and we are going to multiply with this x is equal to 2. This we are going to multiply, and we get is equal to 0 0. So but for lambda is equal to 0, lambda x into 0 is equal to this. Thus x is an eigenvector of a and lambda is an eigenvalue. So let x be an eigenvector of the matrix A, then there must exist an eigenvalue lambda such that Ax is equal to lambda x, or eigenvalue. So this is the equation of the eigenvalue. A minus lambda I x is equal to 0, or sometimes I write lambda I minus A into x is equal to 0. So because if I don't have a mouse, that is why it is difficult to write. So or I can write lambda I minus a into x is equal to 0, or I write a minus lambda I x is equal to 0. Both the things are same. There is no change. Both the equations are same. Only just I multiply here, so I get here. So in some books written like this, and some books write like this. But I follow always this type of method. Lambda I minus a into x is equal to 0. This is the characteristic equation, and from this we can find the eigenvalue. Thus, it follows that x will be an eigenvector of A if and only if B does not have an inverse, or equivalently determinant of B is equal to 0. So determinant of A minus lambda I is equal to 0. It is called the characteristic equation. Yes, I is the identity matrix. So determinant of A minus lambda I is the characteristic equation of A. Its roots determine the eigenvalue. So, but in my class I write, in place of determinant I write lambda I lambda I minus A is equal to 0. This is called the characteristic equation. In a face-to-face class, I told you write this type of things. Lambda I minus A is equal to 0. It is called the characteristic equation. now Now there is a question, a small question. Find the eigenvalues of a matrix A. There is a matrix is given. So I have to write, first of all, what I write? I have to write a characteristic equation. This is the characteristic equation. Lambda I minus A is equal to 0. So what we do, we subtract every element from lambda. This is our matrix, and lambda minus 2 only diagonal element. We subtract only diagonal element. Lambda minus 2 and 12 minus 12 same as minus 1 is same as lambda minus 5 plus. So this is called the lambda I minus 5. It is called the characteristic equation. And then open this determinant. We know how we can open. Just cross multiply this and cross multiply this. So we are getting lambda minus 2 and lambda plus 2 plus 12. This is, so it is a quadratic equation. Lambda square plus 3 lambda plus 2. It is a quadratic equation. Now factorize it. So after that we get 2 factors. Lambda is equal to 1 into lambda plus 2. So the factors are lambda is equal to minus 1 and lambda is equal to minus 2. There are 2 factors. So these 2 factors are called the eigenvalues or characteristic values. So this is the eigenvalue. This is the method to find the eigenvalues. It is called the characteristic equation. From the characteristic equation, I can find the eigenvalue. Now, to find the eigenvectors, there are 2 eigenvectors present in this. One eigenvector corresponding to minus 1 and another eigenvector corresponding to minus 2. There are 2 eigenvectors present. So one by one I am going to find eigenvectors and are corresponding to this. But in a question there is but there is no ask in a question. Question says find the eigenvalues. It only asks to find the eigenvalue. No need to find the eigenvector. In future examples, in after few slides, there is example find the eigenvalue as well as eigenvectors. So this is find the eigenvalues of there is a question, example number 2. Find the eigenvalues of there is a triangle, there is a matrix is written, then find the eigenvalue of the matrix. So as I know, I have to write, this is the characteristic equation. I have to write the characteristic equation. Then after characteristic equation, then we write this, and this is the eigenvalue. Lambda minus 2 is whole cube is equal to 0, and lambda is equal to 2 is, yes, Faz, you are right. I can solve it quickly. But after that, for yes, I know if example 2 can be solved directly from the theorem. But I will still I am not telling you the theorem. I will tell you after 5 or 6 slides. I will tell you that theorem, so that I will solve this thing later on. So yes, you are right. You can directly solve with the theorem. I will tell you after 3 or 4 slides what is that theorem. What that actually that is a property. I will tell you that property later. So right till now I will tell you actual method. What is the method? So lambda is equal to 2 is an eigenvector of multiplicity 3, because of there are 3 values of lambda. Lambda is equal to 2, 2, 2. So that is why I say that lambda is equal to is an eigenvector of multiplicity 3. So computing eigenvector, these are some definitions which is called the characteristic equation, and there are some. So there is a 2 by 2 matrix is given, and same question we have to find the eigenvalue. Determinant of lambda I minus a is equal to 0. There is a quadratic equation and we have to solve this, and we find two roots, lambda is equal to -1 and -2. So there are the eigenvalues are -1 and -2. So there are some methods to find the eigenvalue. Now I will show you how we can find the eigenvectors. In these slides are different. I will show you my method as I told you in my uh, class. So to each distinct eigenvalue of a matrix. Now we are talking about eigenvectors. To each distinct eigenvalue of a matrix A, there will correspond at least one eigenvector which can be found by solving the appropriate set of homogeneous equations. So if lambda I is an eigenvalue, then the corresponding eigenvector xi is the solution of A minus lambda I x is equal to 0. So this is the equation of eigenvector A minus lambda I x, or we can say lambda I minus A into x is equal to 0. This is the equation of the eigenvectors. So these things we have to solve. So from the beginning, uh, we have two eigenvalues. The lambda is equal to -1, one eigenvalue in the previous slide, and lambda is equal to -2. There is an eigenvalue. Now corresponding to lambda is equal to -1, corresponding to lambda is equal to -1 eigenvalue. Now we have to find the eigenvectors. So there is a method. There is a formula of eigenvalue lambda I minus, this is using this formula, lambda I minus a, using this formula lambda I minus a is equal to 0. So I write lambda I minus a, and with the help of this I write the matrix. We get this matrix and open this matrix. So x1 minus 4 x2, x1 minus 4 x2 is equal to 0, x1 is equal to 4t. So x2 is equal to t. So this is the eigenvector. X1 is equal to x1 xt. T, take the t common and t outside, so it is equal to 4 and 1. So with the other examples you can understand clearly. So find the eigenvectors of A. There is a matrix is given. It is a upper triangular matrix is given. So now you can directly find what are the eigenvalues. So the eigenvalues of this matrix is lambda is equal to 2. So now what is the eigenvectors? So the eigenvectors of the matrix is, because of there are three unknowns, 3 by 3 matrix x1, x2, x3. So we take anyone, first we put s, and another time we take t common. First of all we take s common, then another time we take t common. S and t both are not both are 0. Either one is 0, not, you cannot say both are the 0. So there are several properties of the eigenvalues and eigenvectors. So the first property is the trace of the matrix A, designated by trace of A, is the sum of the elements of the main diagonal. So it is called, for example, if we have a matrix and whatever the diagonal elements, the sum of diagonal element is called the trace of A. Now property number 1, the sum of eigenvalues of a matrix is equal to the trace of the matrix A. So whatever the sum of the diagonal sum of the eigenvalue is equal to the trace of A. It is a property of the uh, eigenvalues. And the second property is a matrix is singular if and only if it has a zero eigenvalue. The third property is the eigenvalue of an upper triangular or lower triangular matrix are the elements of the main diagonal. So this is the property that I discussed earlier, previous slides. That is an example of that slide. And the fourth property is if lambda is an eigenvalue of A and A is invertible, then 1 upon lambda is an eigenvalue of A inverse. So these are four properties, and with the help of these properties we can solve many eigenvalues. So there are several properties, but the starting four properties are most more useful or more important. So this property number 5 is if lambda is an eigenvalue of A, then k lambda is an eigenvalue of k A, where k is an arbitrary vector. If lambda is an eigenvalue of A, then lambda to the power k is an eigenvalue of A for any positive integer. So there are several properties of eigenvalue. So this is some properties of linearly dependent and independent eigenvectors. So there are some more examples of eigenvalues and eigenvectors. I will show you after 5 to 6 slides. I will show you the easy examples, good examples. With the help of those examples, you can clearly understand the eigenvalues. Arbitrary means maybe any point, arbitrary constant, any number of points you can take. So over there we can put the arbitrary. Eigenvectors corresponding to distinct, that is different eigenvalues, are linearly independent. So the eigenvectors of lambda is equal to 2 are of the form x is equal to S0t, or S, if we take S common, S outside, if we take S outside from here, then 1, we take 1 here and 0 0 here. If we take T outside from here, then we give 0 0 T. So lambda is equal to 2 has two linearly independent eigenvectors. So there are I'm going to once again repeat what we discussed till now. So first of all, I discussed if A is an m cross n matrix, do there exists non-zero vector x such that Ax is an scalar multiple of x. So there are two things. One is eigenvalue and another thing is eigenvector. So A is defined as a matrix, lambda is an scalar, and x is a non-zero vector. If a equation write like this, Ax is equal to lambda x, then this is a matrix and it is an eigenvalue, Ax is an eigenvalue, and lambda is an eigenvalue and X is an eigenvector. So if anything written like this, then it means eigenvalue and eigenvector. So geometrically, what happens when we say that find the eigenvalue? So it will increase the direction of the vector. lambda x means the value of x till here, and if we multiply lambda to the x, then it will increase the size of the vector. So it is called the eigenvalue. Geometrical interpretation of eigenvalue is this. So verify the eigenvalues and eigenvectors. So these are the few simple examples of eigenvalue. Uh, yes, eigenvalue is you can say eigenvalue is a scalar because of lambda is a scalar. So eigenvalue is a scalar, and eigenvector is a that is a vector quantity. So it is a scalar. So verifying the eigenvalue and eigenvectors. So if there is a matrix is given, A is equal to 2 0 0 minus 1, and the vectors x1 and x2 are given. So first of all, find ax1. It will multiply ax1. So we are going to multiply a into x1, a into x1. So we get 2 0, one vector we get 2 0. And if we are going to take 2 common outside, then we take 2 common outside, then it is called the eigenvalue. Note that it is called the eigenvalue, and it is the rest of the part is called the eigenvector. Or you can write this 2x1. This is the method to write the eigenvector. Similarly, if you are going to write ax2, so there is a matrix and there is a vector, and multiply these matrix and vector, so you will get this one vector. Now take minus 1 common outside. When you take minus 1 outside, then minus 1 is called the eigenvalue, and 0 1 is called the eigenvector. Or you can write minus 1 into x2. So this is a method to write the eigenvalue or eigenvector. Find the eigenvalues and eigenvectors. There is a very simple question. With the help of this question, you can understand clearly. So, as you know that to find the eigenvalue, first of all, we have to write the characteristic equation. Lambda I minus A is equal to 0. So lambda I means from a diagonal element we have to subtract lambda. So lambda I minus A is equal to 0. We have a quadratic equation, and quadratic equation, then factorize it. Then we have two factors, lambda plus 1 and lambda plus 2. Then this is the lambda is equal to minus 1 and minus 2. These are called the eigenvalues. So if you see these are the eigenvalues. If you see the property number 2, recall what is the property number 2 is the sum of the diagonal element is the sum of that the property number 2 is the trace of the matrix is the sum of the eigenvalues. Meaning is that if you are going to add these two things, what you get, minus 2 minus 1 is equal to minus 3. And if you are going to add these two things, trace of the matrix, what you get, 2 minus 5 is equal to minus 3. Okay, so these two things are same. So this is the property number 2 that says that the trace of the matrix is equal to the sum of the eigenvalues. So you can note like this over here. It happens always. If it does not happen, then it is not the eigenvalues. So it is not our point. Now we proceed further. What we say. So we have two eigenvalues. Lambda is equal to minus 1 and lambda is equal to minus 2. So now we are going to find the eigenvectors. First of all, we have to find the eigenvector corresponding to lambda is equal to minus 1. Number 1 point. Then secondly, I find the eigenvector corresponding to lambda is equal to -2. Second point. So there is a long question. If you are going to find eigenvalue and eigenvector, then there is a little bit long question. Now, step number 2, corresponding to lambda is equal to -1. So lambda is equal to -1. We have to subtract. This is the equation of eigenvector. Lambda I minus a into x is equal to 0. This is the equation of eigenvector. So subtract lambda I minus a, subtract the diagonal element over there, then we get -3 and 4 from the previous, as you see from previous over here. This and that are the both are the same thing. So over here I will get -3, 12, -1 and 4, and multiply by x1, x2 is equal to 0. Then x1, or we can write x1 into x2 is equal to. So there are two methods you can solve this. The first method, as we did in a class, that there are two equations. First equation, -3x1 plus 12x2 is equal to 0. And second equation, -1x1 plus 4x2 is equal to 0. There are two equations. I'm not writing, you just note that there are two equations. One equation, -3x1 plus 12x2 is equal to 0, and equation number 2 is -x1 plus 4x2 is equal to 0. There are two equations, and when you are going to see these two equations, or I say that what is the rank of this matrix? If the rank of this matrix is 1. Why? Because of when you are going to multiply row 1 to row 2, then row 1 totally becomes 0, because of it is multiple of row 2 is multiple of row 1, because of 1 3 is a 3 and 4 3 is a 12. So with the help of multiplication you will get row 2 is 0. So the rank of the matrix is 1. So that is why we take only first equation. We take only first equation. That is, our first equation is -3x1 plus 12x2 is equal to 0. So, or you can write 12x2 is equal to 3x1. You can write 12x2 is equal to 3x1, or 12x2 here. So you can write like that. In a class, as I write, there is a you can write x1 and x1. You can write x1 and 3x1, or 3 1 3. इसको cut it out. 3 1 the 3, 3 4 the 12. You can write like this. 1x1 is equal to 4x2. So you can write like that. 4x1 and x2 is you can write 4x2. 4x2, or you can write like that, x1 and 4x2. Yes, x1 and 4x2, because of both are the x1, and such that x1 is a scalar, and take the x common outside. When you take x1 common outside, then you will get 1, 4. 1 comma 4 inside. So this is 1 comma 4 is the eigenvector. So this is the method as I discussed in a class, but here in PowerPoint slides they use a little bit different method, but it is also true. They use this type of method. They will take 4t and t, they will take t common, and 4 and 1 is the eigenvector. So either you can use either this method or that method, but most of the time I prefer to use this method because of, as I discussed you in the class. So, R2, then you can solve this matrix, find the rank of the matrix of the R2. Yani, you are going to multiply row 2 to row 1, and you will get one row is totally 0. So what is the rank? Rank is called the number of non-zero rows is called the rank. So the rank of the matrix is 1. So this is as in we discuss in week 4, week 5, find the rank of the matrix. So there is the same method. Yes, we can reduce the matrix into 1 1 and 0 0. This type of matrix can be formed. So similarly, eigenvector corresponding to lambda is equal to 2 as previous. Now equation number 2, find the eigenvector corresponding to lambda is equal to 2. So lambda is equal to -2. Similarly, lambda I minus 2, this is the formula of eigenvectors, and uh, multiply, and we get this matrix, and multiply x1 x2 is equal to 0. Then again there are two equations. Equation number 4, minus 4x1 plus 12x2, and the second equation is minus 1x1 plus 3x2. Again there is a the matrix has rank 1. That is why we take only one equation, any one equation, either equation number 1 or equation number 2. Let's we assume equation number 2, minus 1x1 plus 3x2 plus 3x2 is equal to 0. Let's we assume this, and with the help of this we get yani x1 is equal to 3x2. From this we get 3x2. So our 3x2. So our eigenvectors are yani 3 and 1. Our eigenvectors are 3 and 1. These are the eigenvectors. So either you can find from this, or either you can find with this. Whatever you like the method, both are good methods. So this is the method to find the eigenvalue and eigenvectors. So one more example of find the eigenvalue and corresponding eigenvectors for the matrix. What is the dimension of the eigenspace of each eigenvalue? So this is the question. So a matrix is given. We observe that this matrix is an upper triangular matrix because of, as we know, the property number 4. If there is an upper triangular matrix, then the eigenvalue is diagonal. The eigenvalue is its diagonal element. So if we observe that it is an upper triangular matrix, so its eigenvalue is lambda is equal to 2. Now find the eigenvectors corresponding to lambda is equal to 2. The eigenvector, eigenspace, you can say eigenspace or say eigenvector, both are the same thing. Eigenspace corresponding to lambda is equal to 2. Similarly, lambda I minus a into x is equal to 0. So subtract lambda I minus a, यानी के lambda I यानी 2 minus 2 is equal to 0. And in a previous matrix, just see there is here put lambda is equal to 2. So 2 minus 2 is equal to 0. and similarly -1 is same, and again put all the matrix. So from with the help of this matrix I formed the whole matrix. And similarly, uh, what is the rank of this matrix? The rank of this matrix is 1. So the rank of this matrix is 1. So I have the equation is minus x2 is equal to minus x2 is equal to 0. This is the equation of the matrix. So we have three unknowns, and so we have three unknowns and three variables and three unknowns. So we assume that there is a value s and t. So any value assume, if we take s common outside, then the eigenvectors are 1 0 0. If we take t common outside, then the eigenvectors are 0 0 1. So this is the eigenvector of the matrix. S0T are the eigenvectors. So similarly, if an eigenvalue lambda1 occurs as a multiple root k times for the characteristic polynomial lambda1 has a multiplicity k, the multiplicity of the eigenvalue is greater than or equal to the dimension of the eigenspace. Some another example, find the eigenvalues of a matrix A, find the basis for each corresponding to eigenvalue. So find the correct, or first of all write the characteristic equation lambda I minus a. It is the characteristic equation, and solve this. So we write this and we are going to solve this. We have this roots, and the roots of this equation, lambda1 is equal to 1, lambda2 is equal to 2, lambda3 is equal to 3. So these are called the eigenvalues of the matrix. Now find the eigenvectors. So one by one I am going to find. First of all, I find the eigenvalue corresponding to lambda1 is equal to 1. Then after I find the eigenvector corresponding to lambda2 is equal to 2. Then after I find the eigenvector corresponding to lambda is equal to 3. So first one I will go to find lambda1 is equal to 1. Find the eigenvector. So for lambda is equal to 1, the eigenvector is lambda I minus ax is equal to 0. Put in place of lambda is equal to 1. Put here 1 minus 1 is equal to 0. So I get 0 here, and whatever the matrix is, so I get this matrix and it will is equal to 0. Similarly, solve this matrix with the help of this. So we have we have four variables x1, x2, x3, x4. So we take st over there. We take when you are going to solve this, we take minus 2t s and 2t t. So this is an eigenvector. So if you take s common outside, then you will get this, and t common outside, then you will get this. S and t are non-zero. Is a basis for eigenspace A corresponding to lambda is equal to -1. Similarly, find the eigenvalue corresponding to lambda2. So from this same thing, this is the equation of the eigenvector, and subtract 2 minus from there main, and we get 1. The main equation lambda I, this is the main equation. Subtract from here. We get 1 here. 2 minus 1 is 1 here, and rest of the matrix are same. And similarly, I get this thing 5tt. So first of all, I take t common outside, then we have 5 1. It is called the eigenvector. Similarly, lastly, I find the eigenvector corresponding to lambda is equal to 3. So again, I write in place of 3, So lambda minus 3, it is the equation of the eigenvector, and find lambda. Lambda is 3. The 3 minus 1 is 2. Our main equation is this is our main equation. So lambda minus 1, yani 3 minus 1 is 2. Similarly, lambda minus 1 is 3 minus 1 is 2. So as we see in that slide, so it is 2 and it is 2, and similarly here we get the same matrix over here, and open this matrix, we will get this eigenvector. And or you can write t, take common outside, so inside we will get 0, -5 and 0. So this is a basis for the eigenspace of A corresponding to lambda is equal to 3. So there are several examples eigenvalues of a triangular matrix. If A is an n by n triangular matrix, then its eigenvalues are the entries of its main diagonal. Yes, for example, A is an lower triangular matrix, so the eigenvalue of this lower triangular matrix is 2. These are the eigenvalues of this lower triangle. 2, 1, minus 3. You are right. 2, 1, minus 3 are the eigenvalues of this triangular matrix. Similarly, what are the eigenvalues of this matrix? The eigenvalues of this matrix are the diagonal elements. The diagonal elements are -1, 2, 0, 4, -4, and 3. These are the eigenvalues. Directly you can write. No need to calculate it. Directly you can write the eigenvalues by the property number 4. Now the last thing is, what is diagonalization? So the diagonalization is a procedure. From here we are given a matrix. So first of all we have to find a character. Well, first of all we have to find a eigenvalue. Then we have to find the eigenvectors. Then with the help of eigenvectors we can form a diagonalization. So let's see what is diagonalization. For a square matrix A, does there exist an invertible matrix P such that P inverse AP is diagonal? Diagonalizable matrix, a square matrix A is called a diagonalizable if there exists an invertible matrix P such that P inverse AP is a diagonal matrix. P is a diagonalized A. So this is the P inverse AP is a diagonal matrix. If there exists an invertible matrix P such that P is equal to P inverse AP, then two square matrix A and B are called as similar. The eigenvalue problem is related closely to the diagonalization problem. So there is a theorem: if A and B are similar n by n matrix, then they have the same eigenvalues. So if there are two similar matrices, then they have the same eigenvalues. So there is a question: diagonalize the matrix. A matrix is given 1, 3, 0, 3, 1, 0, and 0, 0, -2. A matrix is given. So find the diagonalize of this matrix. So there are this is a very big type of problem. So what step we have to proceed? Step number 1, we find the eigenvalue of this matrix. So this is step number 1. Find the eigenvalue of this matrix. So we know to find the eigenvalue, we have to write the characteristic equation. Lambda I minus A is equal to 0. So we subtract this lambda minus 1 from the main diagonal element. We find lambda minus 1, lambda minus 1, lambda plus 2, and solve this matrix, we get lambda minus 4 and lambda plus 2 whole square is equal to 0. So the eigenvalues are lambda is equal to 4 and lambda is equal to minus 2 and minus 2. So these are the eigenvalues. Now the step number 2. Now the step number 2 is find the eigenvectors. Find the eigenvector corresponding to lambda is equal to 4. Then find the eigenvector corresponding to lambda is equal to minus 2. So first of all, I find the eigenvector corresponding to lambda is equal to 4. So the eigenvector lambda is equal to 4 is 1, 1, 0. You can find at your home how I get this 1, 1, 0. We can get as a previous question. You can see how we can obtain this 1, 1, 0. Now the eigenvector corresponding lambda is equal to minus 2. Corresponding lambda is equal to minus 2, I get the eigenvector 1 minus 1, 0. Now similarly again the eigenvector corresponding to lambda is equal to minus 2, I get 0, 0, 1. There are 3 eigenvectors corresponding to lambda is equal to 1, minus 2 and minus 2. So combine these eigenvectors. So when you are going to combine these eigenvectors, we get the same, we get this matrix. This is this 1, 1 minus 1, and this is the eigenvector corresponding to lambda is equal to 1. So this is the main matrix. This is the matrix combination of the eigenvectors. It is called the combination of the eigenvectors, or we say it is P. So we have to find P inverse AP. So if P is equal to this and P inverse AP is equal to this minus 2, 0, 0 and 0, 4, 0, and what happened? So this is P inverse AP is equal to 4 minus 4, 0, 0 and minus 2, 0, 4, and just we'll rearrange these things and we get P inverse AP is equal to this. So this is called the diagonalization. This is diagonalized. As we observe that the diagonal element 4 minus 2 minus 2, it is a diagonalized. So this is the procedure to write the diagonalization. A matrix that is not diagonalizable, show that the following matrix is not diagonalizable. We have given a matrix and find the eigenvalue. Lambda is equal to 1 is the eigenvalue, and find the eigenvector corresponding to lambda is equal to 1. There is eigenvector 1, 0 is eigenvector, and A does not have two linearly independent eigenvectors, so A is not diagonalizable. So we cannot diagonalize it because of it has only one question. The question number 3, find the diagonalization. It is a 3 by 3 matrix. So again, step number 1, find the eigenvalue. Eigenvalues are 2, minus 2, 3. Now corresponding to eigenvalue, find the eigenvector. So the eigenvector corresponding to lambda 1 is minus 1, 0, 1. This is the eigenvector first. And again, eigenvector corresponding to lambda is equal to minus 2 is P2. Similarly, the eigenvector corresponding to lambda is equal to lambda 3 we get P3. Now combined P1, P2, P3. P1, P2 and P3. Combined all these things. So when you are going to combine all these things, we get a matrix P such that P inverse A and P is equal to 2 minus 2, 3. If you are going to multiply this thing, then we get 2 minus 2, 3. It is the diagonal matrix. So eigenvalue of a symmetric matrix. If A is an n by n symmetric matrix, then the following properties is true. A is diagonalizable. All the eigenvalues are real. So there are several properties, and some rest of the proof. So these are the this is the end of the lecture. And do you have any question about this? Just tell me, Fahad. Yes, if we multiply the matrix by its inverse, we get the identity matrix. No, you are right. Uh, okay, see these PowerPoint slides, and if you still you have any problem, then you can discuss me later. Okay, okay. These PowerPoint slides are available on the Blackboard. There is extra material. Maybe you can find now or after half an hour, after 1 hour, you can find over there. I already uploaded. Okay, and good night. Take care.